Okay, hi everybody. Okay, so in this module, what we're going to do is we're going to look at how to obtain an all-integrator block diagram from state space representation, and then we're going to look at how to obtain a transfer function from state space representation or from state space model. Now, in the previous module, we looked at 4 different ways of representing a system using ordinary differential equation, using a transfer function, using all-integrator block diagram, and using state space model. What we're going to be doing today first is we're going to look at how to obtain an all-integrator block diagram from state space representation. So the first topic is state space model to all-integrator block diagram. Okay, now we know for each state variable we need to include one integrator. So for each state variable we need to include one integrator. And the state equations that we have in the state model specify for us how the integrators are connected. So the state equations specify how integrators are connected. To each other, and also how they are connected to the input. And finally, the output equation tells us how to construct y of t from the state variables. Okay, so again, each state includes an integrator. The state equations tells me the relationship between the states and how they're connected together, and the output equation will tell me how the output is constructed, how the output y of t is constructed using the state space equations. So let's do an example, the examples that we started before, and see how we can obtain the all block diagram using the state space representation. So the previous example we had, the mass damper example. We have x1 dot, x2 dot equal to 0, 1, 0, negative b divided by m multiplied by x1, x2 plus 0, 1 over m multiplied by u of t. And we also have x1 dot, or so from these equations, from these state equations, we can write x1 dot is equal to x2 and x2 dot is equal to negative b over m multiplied by x2 plus 1 over m, this is m, multiplied by u of t. So since we have 2 states, then we're going to need 2 integrators. Since we have 2 states, we need 2 integrators. So therefore, I'm going to have a first integrator, a second integrator, and the first integrator is going to have at the output x2 and the input x2 dot, and the second integrator is going to have at the output x1 and the input x1 dot. Now using the state equations that we have above, x2 is equal to x1 dot. So x2 or x1 dot is equal to x2. So this variable here, x2, is equal to x1 dot. And x2 dot is equal to negative b over m multiplied by x2 plus 1 multiplied by u of t. So therefore, using the equations above, I can construct this diagram. I can have this integrator here, and this is x1, this is x1 dot, this is the second integrator, this is x2, and x2 is equal to x1, x2 is equal to x1 dot, and x2 dot from this equation that I have above is equal to 1 over m multiplied by u of t. So this is u of t. I have to multiply it by 1 over m, and this is positive, and then I have negative b over m multiplied by x2. So I can take x2, multiply it by b over m, and then add it with a negative sign, so to obtain x2 dot. x2 dot is equal to u of t multiplied by 1 over m minus b over m multiplied by x2, which is what I have at the equation there. Okay, now we still have the output. The output equation from the state space representation, the output equation tells us that y of t is equal to x1 of t. So therefore, I can just come to my representation that I have here, and this x1, I'm gonna just write it here because it's the output of the integrator, and I'm just gonna have the output y of t to be here. Y of t is equal, this signal, the output of this integrator is x1, and that is my output y of t. So here we see that we can obtain the all block diagram directly from the state space representation. Depending on the order of the state space representation, we're going to have as many integrators as the order of the state space representation, and as many as we have states. So the order is equal to the number of the states. So in this case, we have a second order, we have 2 integrators. If we have 3 states, we're going to have 3 integrators. 4 states, we're going to have 4 integrators. And then using the equations that relate the states to each other, we can connect the integrators' output and inputs. And then using the output equation, we can also indicate where the output the output is in the all block diagram, all block integrator diagram. Okay. Next, we're going to look at how to get a transfer function from state space model. So what we're going to look at next is state space model to transfer function representation. Okay, so let's look at the first method, and we're gonna call this this method, we're gonna call this the long approach. So what we're going to do is first we're going to obtain an all integrator block diagram. So obtain all integrator block diagram. And then we're going to set initial conditions to 0. and then we're going to take the Laplace transform of the signals. And then we're going to obtain the transfer function. Find the transfer function. Okay, again, using the example that we just did, let's try to do it so it fits all on this page. So the state space representation again was x1 dot, x2 dot equal to 0, 0, 1, negative b over m multiplied by x1, x2 plus 0, 1 over m multiplied by u of t, and we have y of t equal to 1, 0 multiplied by x1, x2. Okay, so we're going to obtain, so on the right side I'm going to follow these steps. We're going to obtain the all integrator block diagram. So we had u of t multiplied by 1 over m, and then we have an integrator, we have another integrator, and we have y of t, and then I have b over m, and this is a negative sign. Okay, now of course each one of these integrators have initial conditions. So even going back here, I have initial conditions that I can also add here. So I have x2 of 0 here, and I have x1 of 0 here that I can add. Okay, so the same thing here. I have x2 of 0, I have x1 of 0, the initial condition of x2 on x1. And this is x1, and the input is x1 dot, which is equal to x2. Okay, so following the procedure that we just laid out, I'm going to take the Laplace transform. I'm going to set the initial conditions to 0. I'm going to take the Laplace transform. U of t is going to give me u of s. This is a constant, is going to stay a constant. And then I have an adder. An integrator in the Laplace is going to become 1 over s. And another integrator is going to become 1 over s. And I'm going to have y of s. And I'm going to have the feedback loop, which is b over m. And this is a negative, this is positive. Okay, so we take in the Laplace transform of this, and then I can simplify this feedback loop. I can write this as u of s 1 over m, and I can get the equivalent of the feedback loop, which is going to be 1 over s plus b over m. We did this in the previous module. You can go back to it, or you can check it if you like. This is 1 over s, this is y of s. Of course, we set here, after we took the Laplace transform, we set all the initial conditions to 0. The transfer function is defined with initial conditions equal to 0. So all the initial conditions are set to 0. I had the block diagram in the S domain, and then I simplified the block diagram. And if I look here, I can write that y of s over u of s is equal to 1 over m multiplied by s plus b divided by m. Okay. Okay. So this is the long way of obtaining the transfer function from the state space representation. The second method is to look at the state space representation, x dot equal ax plus b multiplied by u, and then we said we have y, that is c multiplied by x. Now in general we also have another matrix D multiplied by U. So what we're going to do is we're going to take this state space representation and we want to obtain the transfer function from this state space representation. So what we're going to do is we're going to take the Laplace transform and of course so far we did not talk about these, so we can keep it or we can ignore it for the time being, either way. So we're going to take the Laplace transform of this state space representation and we're going to set initial conditions to 0 . So if I do take the Laplace transform of these equations, I'm going to get s multiplied by x equal to a multiplied by x, and these are all of s because we're taking the Laplace transform, plus b multiplied by u of s. And the output, we're going to have y of s equal to c multiplied by x of s. And if we have the matrix D, we're going to have D multiplied by U of S. Okay. So then, what we're going to do is we're going to solve this equation for x of S. So this equation, I can write it as S of x, S multiplied by x minus A multiplied by x of s equal to b multiplied by u of s. Now remember, A is a matrix, so therefore I can take x of s as a common factor, and I can write it as the following. I can multiply s by the identity matrix minus A multiplied by x of s equal to b multiplied by u of s. Again, if I multiply again, I'm going to get s multiplied by the identity multiplied by x is just going to give me sx. And a multiplied by x is going to give me ax. Okay. Now what I'm going to do, so again, I is the identity matrix. What does that mean? If I have a 2 by 2, it's 1, 0, 1, 1, 0, 0, 1. If I have a 3 by 3, it's going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. The diagonal terms are 1, and all the other terms are 0. Okay, so what I'm going to do next is I'm going to take x here, and I'm going to write this equation in terms of s. How do I get x term alone here? Since it's multiplied by this term, I'm going to multiply by the inverse of it. So what I'm going to do is I'm going to take multiply by si minus a inverse multiplied by si minus a multiplied by x of s, and this is going to equal to si minus a inverse multiplied by b multiplied by u of s. The inverse multiplied by the matrix is going to give me the identity, so therefore this is going to give me x of s equal to s multiplied by I minus a inverse multiplied by b multiplied by u of s. Again, the matrix multiplied by the inverse of it is going to give me the identity. The identity multiplied by x of s is just going to equal to x of s. So now that I have x of s, I can take x of s and substitute it in the equation for y of s. So I can take the equation here of y of s, and I can say that y of s is equal to c multiplied by x of s, but x of s is given by this. So I can write it as c multiplied by s multiplied by I minus a inverse multiplied by b multiplied by u of s, and plus, if I have the D matrix, plus d multiplied by u of s. Now I can also put these terms together and just keep u of s out. So I'm going to have s multiplied by I minus a inverse multiplied by b, and then plus d, and all this multiplied by u of s. So if I look here, I notice that I am expressing I can express y of s over u of s, and this is equal nothing other than c multiplied by si minus a inverse b plus d. And this is the transfer function. Okay, so let's go back to our example and plug in some numbers and see how we obtain the transfer function. Of course, in our example that we have for the state space representation, the d was equal to 0. The output did not depend directly on the input. So for the example that we started for the mass damper, the D matrix is null, it's empty. So for our mass damper example, we had the A matrix was equal to 0, 1, 0, negative B over M, and the B matrix was equal to 0, 1 over M, and the C matrix was equal to 1 and a 0, and the D was equal to 0. So therefore, in order to obtain the transfer function, I need to calculate Si minus A, and then I need to obtain the inverse for it. So the first step, we're going to calculate Si minus A. So what is this Si minus A equal to? I'm going to have S multiplied by, of course we have a 2 by 2, so the identity that I'm going to use is 1, 0, 0, 1. This is S multiplied by I minus A, which is 0, 1, 0, negative B over M. Now if I multiply and subtract, what am I going to get? S is going to the first term is going to be S minus 0 is going to be S. S multiplied by 0 minus 1 is going to be negative 1. S multiplied by 0 is 0, minus 0 is a 0. S multiplied by 1 minus B over M is going to give me S plus B over M. Okay, so next we need to calculate the inverse. So we need to calculate Si. Of course, S here is a small letter, even though I wrote it as capital. Si minus A inverse. How do I obtain the inverse of a 2 by 2 matrix? So let's put it on the side here. So if I am given a matrix F that is equal to F11, F12, F21, F22, then the inverse of this matrix, F inverse, is going to equal to 1 over F11 multiplied by F22 minus F12 multiplied by F21, and then I'm going to swap F22, F11, and I'm going to take a minus of f12 and negative of f21. Minus minus, these two terms and these two are swapped. Okay, so therefore, because this inverse is going to exist only if this term f11, f22 minus f12, f21 is not equal to 0. If this determinant is not equal to 0. Okay. So therefore, here we're assuming that f11, f22 minus f12, f21 is not equal to 0. Otherwise, we will not have an inverse. Now, of course, notice here that if I take f multiplied by f inverse, this is going to equal to f inverse multiplied by f, and it's going to equal the identity. And it's going to equal to 1, 0, 0, 1. Okay, so going back to our example, if I want to calculate Si minus A inverse, this is going to equal to 1 over, I'm going to have to multiply S multiplied by S plus B over M minus 0 multiplied by a 1, so therefore minus a 0. And then I'm going to reconstruct this matrix by swapping S plus B over M, and this is going to be an S, and then I'm going to multiply by minus sign the 1 and the 0. The 0 is going to stay a 0, and the negative 1 is going to become a 1. Now if I multiply these together, I'm going to get, if I multiply, of course this is negative minus 0, is going to just disappear, the 0s will disappear. 1 over S multiplied by S plus B over M multiplied by S plus B over M is going to give me 1 over S. 1 over S multiplied by S plus B over M multiplied by 1 is going to be S multiplied by S plus B over M. And then 1 over S multiplied S plus B M by 0 is going to give me a 0. And then 1 over S multiplied by 1 over S multiplied by S plus B M multiplied by S. S with S is going to cancel. I'm going to get 1 over S plus B over M. And therefore, if I go to the formula that I had, we're going to get the inverse multiplying C by S I minus A inverse multiplied by B, and therefore y of S divided by u of S is going to equal to C multiplied by Si minus A inverse multiplied by B. And therefore, if I substitute, the C is equal to 1, 0, and Si minus A inverse is 1 over S. 1 over S multiplied S plus B over M, and then 0, 1 over S plus B over M, and then multiplied by B. B is 0 and 1 over M. Okay, so if we multiply these, this is going to give me 1 over S, and then this is going to give me, okay, so the way we multiply these, I'm going to take this, I'm going to multiply it by these two, term by term, and then I'm going to multiply it by these two. This is a 1 by 2 multiplied by 2 by 2 is going to give me a 1 by 2. Okay, so therefore, if I multiply these, continuing on the next page, I'm going to get 1 over S and 1 over S multiplied by S plus B over M multiplied by 0 and 1 over M. Again, 1 is going to multiply 1 over S, 0 is going to multiply by the 0, 1 is going to multiply 1 over s plus 1 is going to multiply 1 over s multiplied by s plus b over m, and the 0 is going to multiply the 1 over s plus bm. So therefore I'm going to get 1 over s multiplied by s plus bm. And then when I multiply these, this is 1 by 2 by multiplied by 2 by 1 is going to be 1 by 1, and I'm going to get 1 over m multiplied by s plus b over m. Again, this matrix is 1 by 2. This matrix is 2 by 1. When I multiply them, the result is going to be 1 by 1, which is this term here. Now this result that we just obtained here is similar to what we obtained at the beginning of the lecture. 1 over ms multiplied by s plus bm. The same results. Okay. I'm going to stop here. In the next module, we're going to look at the state space analysis, and we're going to look at general method for obtaining an all integrator block diagram from a transfer function. Thank you, everybody.